Hello everyone. Today I would like to, or we would like to present the results of our work that we were doing here over the last few weeks. We are involved in dialogs, so we named our team Kea Dialog. The motivation. Imagine that the contact centers have a huge quantity of data and they don't know what is inside. Average agent can process or create like 5 hours of speech data a day. That is roughly 100 hours a month. And imagine that there is no one agent in the call center. There are many, and there are many companies. So it's huge quantity of data. And what else? The agents are trained to serve to customers or to sell some goods. So it's structured. Then in these days, companies would like to deploy AI agents, but if they don't have enough insight, it is hard. It is hard because someone needs to come, listen it, and it is very risky because there is a risk that the AI agents will be developed for something else that the company really needs. So our goal is to extract the information from the data automatically, give the insight to people, and it can be in graph structure, and the skeletons or the graphs can be used to design such AI agents. And also the extracted informations can be used for tasks like quality control, call script adherence. So what is our goal? Our goal is to really extract dialog structure from the data in a human readable form, and to have algorithms and tools to be able to do it for any data. So you can see that there is some flow. There is, for example, a greeting at the beginning of each call. Agent or user can ask for info, for example, or for some service, for example, to book train, then the agent books the train, shares the information, and finally he says goodbye. Here is our team. I won't go through all the people, but what I'm really happy about that the team is well balanced between academia and industry. Basically, the industry said it is really important topic for us. We would like to work on it, and the academia said yes. This is a hard enough problem. This is a challenging problem. We would like to work on it. We split our team to some parts to be able to attack the problem. So we were working with data, so we needed to prepare the data for us, but also to create some example dialog structures. Then it's about speech. We needed to convert to speech to some representation to encode the speaker turns, encode dialogue history. So this is this dialogue embedding part. Then we realized that the embeddings are probably not enough, and we need to go further, extract more information like name entities, slot values. Therefore, we have this downstream task subgroup. After that, we have the dialog structure discovery subgroup, and then we would also like we wanted to go closer to application tasks, basically how to align actual dialogue with the dialogues that happen in past, how to predict next turn or advise the agent, this is this similarity scoring subgroup. And of course, we need to evaluate the algorithm somehow. So there was a group of people involved in evaluation. So the outline of the talk, basically we will go through the sub-themes, and we will go in this order that you see on the slide. And now I would like to handle the mic to Patricia. She will tell more about data. And on the slides, you can see names. Basically, if you go through the presentation later, or you meet the people around, these are the people that have the closest that are the closest to the topic. Feel free to ask them. So thank you.
Hi everyone, I'm Patricia, and I will take you through the datasets and augmentation part. So we will discuss some of the purposes that we use the data for and their requirements. Then we will look at some challenges that we had with the data. We'll have a brief look at augmentation. We will look at Allomedia data, which is a dataset which has not been released yet, but has been extremely helpful for us, and we do have some annotation schemas for it. And then we will look at the expectations of the output, because data is not only our input, but also the thing we produce. So, in terms of requirements, if you train embeddings, then obviously you need lots of data. And there are no real requirements of additional annotations, such as slot values, named entities, and so on. So you can actually use a lot of data for this purpose. Then, for training joint speech embeddings, we have used the slurp dataset. And for ASR with long dialog context, we used Fisher. And then for the dialog structure discovery, we started by using MultiWAS. But then we saw that it's synthetic. Many LLMs have already been trained on it. So we moved a little bit towards the Allomedia data that I will present later. So some of the challenges. There are many dialog datasets, and each of them has some different format. They have some different type of annotation. Some of them are annotated with the goal of the dialogue. Some of them are annotated with the slots and their values. And it's kind of difficult to put all of this together. And there are some unified formats, such as convlab. Unfortunately, it doesn't have that many data sets, and it's only unified on the top level and not bottom down. And also, one of the data sets, or like a collection of data sets that was released during the work, was Dialog Studio by Salesforce. Unfortunately, this has no normalization. So while it can help you find some data sets, it will not really help you load the data and use it. So if you want to use more data, we need to think about it carefully, because we need to normalize everything. And we do have some scripts for that in our package, which will be released after the workshop. Then there's a lot of data for written task-oriented systems. Unfortunately, there's not as much for spoken dialogue systems. However, this has improved massively over the past year, as speech tracks for MultiWAS were released in the fall of last year, and also SpokenWAS was released a couple of months ago. Then, of course, yes, Sanjeev? Oh, yeah, of course. So WAS stands for Wizard of Oz, which means that the datasets were collected by having two people talk to each other. The user thought he was talking to a machine, but in truth, such as in the Wizard of Oz, there was a person behind the machine. So you just have two crowd workers talking to each other. And so in the MultiWAS, text was first, and then crowd workers were used to get speech. And in the SpokenWAS, speech was first, and then it was transcribed. So Then there's also a huge gap between synthetic and real-world data. Since synthetic data sets are, as I mentioned, collected by crowd workers who are not really invested in those problems, so the conversations tend to be more straightforward and sort of easier, cleaner. However, the real-world data is much, much more difficult. And so we targeted this challenge by using Allomedia data, which is somewhere in between. It was also collected by crowd workers, but it's closer in domain to our purposes of call centers and trying to resolve some problems in some processes. And also, some of the industry members of our team had access to proprietary data that they couldn't share with us for research purposes. However, they could evaluate some of the methods on this data. So we do know how hard it is. And then finally, LLMs have been trained on many publicly available datasets, such as multi-was. So if something is working on multi-was and it is using some LLMs, then it doesn't really mean anything for other datasets. So we address this by using newer and publicly unreleased data, such as the Allomedia dataset. So quickly for the augmentation, we have implementation of paraphrasing, ASR-like errors such as close homophone swap, and then speech-related disfluencies such as hesitations and repetitions of some words. However, due to time, this was not our main priority, so we didn't use it that much. So for the Allomedia dataset, it's a dataset which has been collected by Allomedia. It's simulating a client calling about a purchase that did not go through. One dialogue is roughly 5 minutes, and in total the dataset has 15 hours and 41 minutes of dialogue. This was done last year in November, and also we have some gold data for this dataset, so we have the manual transcriptions and also the detection of named entities also classified into slots. So on top of all of this, we started our own process-based annotation, where we looked at the events which could happen, which is, for example, the agent asks the client to provide their name or to state the problem, and so on. So usually we have the agent asking for some information and the customer providing the information. On a more fine-grained level, we also do have annotations of events, which is something happens, so someone states something, then there are some actions being taken as a result, and also we do have the intent values annotated as well. So far we have 70 dialogues annotated out of 246. And so in total, there's only one type of customer request, which is my payment did not go through. What happened? I would like to fix it. 8 types of events, 22 types of actions, and 65 types of intents. So as the data we are striving to produce should then be helpful in analysis, we need to pay attention to what someone should be able to find in the data. So the data should be able to help to answer the questions, what's going on in the business right now? And then this information can then be used to improve what's going on in the business. So as with most things, it was not really easy. And it's not really easy to define the dialogue states. There is no one right answer. So we reached a consensus. It's also, we needed to think about what it means for the dialogue states to be human interpretable. Because if we discover them automatically, we mostly, if we have some clustering methods, then we need to also know the number of clusters on the input. So the results might not be interpretable. And it's important for us to think about how to look at that. Also, human dialogues are incredibly varied. So this is, of course, difficult. And in the end, we want to end up with something that we can use, that represents the conversations well, and which can possibly get good performance on downstream tasks. So the way we did that, and I got into that briefly before, but there are some events, such as, for example, the agent asking the client for some information. There are some actions, so the agent needs to do something to actually fix the mistake that the client is talking about. And then we form processes by having a sequence of such events. And so if we want to look at existing processes, it's also important to look at the order of actions, because if you have something like technical support, it does matter if you turn the computer off before turning it on again. However, if you have a system which recommends a restaurant, then you don't really care if they ask about the type of cuisine first and then the price range or the area, because it doesn't matter. And we need to define what happens to sort of get the hope of having something which is human, interpretable, and usable. So this is what resulted as a result of the annotation. This is a graph formed on 70 dialogs, and we can see that in the first part, which is intent, that is the agent asking the client about what their problem is, how they might help them. We can see that sometimes they need to ask them to repeat themselves, but usually they move forward to asking about the information of the user. So for example, their name, and then sometimes more information is necessary. For example, their date of birth, their address. So we need to fill this in before we can continue the dialogue. And then we can proceed to asking about the order, what didn't go wrong, what went wrong, and what happened, fixing it, and so on. So this is something that we would like. This is something we can analyze, and this tells us about how the processes go and what's going on in the company. So some of the other ways to look at this is you can also look at the dialogues which are short. So they manage to get their goal finished in a short amount of time. You can learn from this and see how you can make the process more efficient. You can also look at the longest dialogues to see what's wrong there, if you can fix anything, if there's maybe some bottlenecks in the process. And you can also look at the typical dialogue by looking at the most frequent path. So to sum up for the data part, we first need to have a unified framework for handling data sets, which enables us to work with the data, to harness the volume of the data, and have good embeddings. Then we need to have data sets which have the right amount of annotation necessary to have dialogue structure discovery algorithms. Also, it's very, very beneficial to have handcrafted graphs which tell us what the goal looks like and what we should strive to reach using automatic methods. We have overpassed the data contamination problem by using data which was definitely not somewhere in LLMs. And furthermore, we have moved from the simpler data to the more complicated data which is closer to the real world scenarios. If there are any questions for the data part? Okay, Sanjeev? Okay.
So the part where you talked about creating the ground truth graph,
Yes.
right? That looked to me like a problem where you have a sequence of tags about what kind of activity is going on, and you have 70 of those. one for each dialogue in the training in your data that is hand labeled, and then you make a graph out of that. Is that how it was done?
Oh, no. So this is the sum of 70 dialogues. So there are 70 dialogues in this.
No, that's what I'm saying. So basically, each of those dialogues will follow one of these paths.
Yes, precisely.
Right. Okay. So this one basically is some kind of finite state acceptor, and what I'm thinking is this clearly accepts all 70 of these dialogues. Each of them has a path through it. But future dialogues may have other things going on in them. So how does this generalize to future dialogues? Because what I'm thinking is some customer might provide both the intent and the user info in one turn. And so, or other things could happen. I'm just imagining that dialogues, once you start getting thousands of them, will have other weird things happening. So how does one generalize this? Is there a way to say we will do something which makes this more, like accept even more sequences than these 70?
One answer which comes to my mind, and it's something that Mira will talk about later, but to answer your question, we do have a framework where we look at the slot values. So we look at the information that was given by the user or the agent. And if they provide several information at once, then we break it apart into several pieces and consider all of the possible orderings in case it.
Yes, so here we were thinking about what is our target. So in the data part, it is easy to add more intents, more actions, but this is addressed later in the automatic methods, because there we can extract these passes or do pruning of the graph and different operations.
Thank you.
Okay. So in case there are no further questions, then I would pass the mic to Sergio to talk about embeddings.
Hi everyone, we're Sergio and David. We will take care of the dialog embeddings part. So let's move on. Let's start with the motivation. So basically the motivation is to have a way to represent dialogue history or dialogues, or either individual churns or complete history. And to be represented in such a way in this latent space that similar calls or similar turns, let's say, will be closer in this space. But this is like a really, what do we mean by similar, right? So this is quite complex, because what notion of similarity are we using, right? We're talking about context, similar because they appear in similar context. It's similar because semantically they are similar, or because they share the same intent, or turns have the same dialogue act, etc. Right? And also it will depends the similarity measure that we use to kind of will shape the space, right? This space. And this also is slightly related to the previous question, in the sense that if we have this notion of similarity, then we can somehow cluster this space to find like really dense sections in this space. But of course, depending on what we define as similarity, this could be used, for instance, if we cluster dialogues, we can try to discover states. If we cluster, let's say, turns, maybe we can try to find actions or edges in this graph. And depending the similarity used, it will be kind of the granularity that you will get, right? Or what this cluster may represent. So before we go to the actual implementation, let's first see how people is addressing some of these questions with the 3 of the latest dialogue encoders that are out there. The first one is ThoughtBird, was published in 2022, papers in the bottom part. Okay. And this, as the name suggests, ThoughtBird is just a bird, but they have added special tokens for identifying system and user turns. And they have replaced the next sentence prediction task in the pre-training to get the encoding of the classification token by what they call a response contrastive loss that basically it's defined by this equation that let me explain real quick. So basically here you have it uses in batch negatives. It means that each batch to define a T where to cut to consider the context of the conversation, and then you get the response, which is the next turn. So you have all positive pairs in the batch. Like for this context, this is the next response. For this context, this is the next response, and so on. And then basically, since all of these are positive pairs, you need to get the negatives and the anchors, right? So the anchor will be this, given this context, the positive is easy, we have it here, and the other ones in the batch will be the negatives. The same with C1. In this case, this is the positive, the negatives will be the other two, and you continue to do this. Basically, it's the same as having this. When you multiply the context matrix with the response matrix, you have here the dot product of all of these contexts with all of these responses, and basically of the embeddings. Here we have the embeddings of the context, the embeddings of the responses, and we want to maximize the diagonal while minimizing the others, right? So that's what this softmax is applied row-wise, and that's the trick that it's doing. So here, going back to the question, the metric, here we are using dot product. So it means in this space, or the notion of this dialog being similar to this dialog, or this turn being similar to the other turn, it will be given by the context. One call will be similar to the other if it's expected to have similar response. And turns will be similar if they appear in similar context. And here, the matrix will means that in this space, we're talking about alignments, right? We're making the context, the vector, the embedding some context and the embedding of response to be more aligned and disaligned for the others. So, okay, let's move to the next one. The next one was released after ThoughtBERT, and it builds on top of it. It was trained with the same, pre-trained with the same data sets. It's 1.4 million utterances. And it's a simplification, but it worked better in practice. Actually, this one was the embedding used for winning the latest DSTC competition 11, task 1 and 2. So instead of considering the context, the entire dialogue history, they simply consider in context the previous utterance. So the positive pairs, you have a sliding window, so positive pairs will be current turn, next turn, and then you move the window, and then you have the previous one here is the one here, and the next one, and it's a simple sliding window. This is interesting because you mean, well, it's simpler, and you can say, well, but this is only learning presentation of a turn. But indirectly, it's also somehow learning the dialogue, because this is a sliding window. So when you move this embedding closer to this one, but then you also move this to the other one. So it's like a change. So you somehow have also influenced all the turns in a conversation. So all the turns in a conversation will move closer to each other. And they replaced the previous loss by this hard negative sampling strategy, which is similar to the previous one, but it's weighted. So it means that negatives that are closer to the anchor will be pushed far away. So that's basically what it is. And here we have the papers in which the loss was defined, and where the architecture is defined. It's using the same one. This is BERT, the same as the previous one, but they don't use special tokens. And just the last one, it's a generalizable T5-based dense retriever. It was not published directly in the context of dialogue, but still was trained on 2 billion question answering pairs from Reddit and Stack Overflow, which it's close to resembles dialogue in social media. And it's following the same pattern. You have here as dual decoder. The previous one were also B encoders, a dual decoder, right? Because you need to create the embeddings of, remember, the context and response. So you need to encode both. Oops, sorry. Sorry, right there. So here you, instead of giving the turn or the dialogue history, you give the question, and you also the answer, and you make them closer or far apart if this question correlates. It's the this is the response to the actual question, and if not, the bush far away. So basically, when Peter, we joined to the team, he basically suggested that he had a good experience being part of the original Kali team. So he wanted to kind of said, well, guys, if you think about it, it would be nice to have some sort of toolkit after workshops. So take this in mind, try to consider what you do, try to have some sort of toolkit. So that's why we decided to, from the beginning, try to think of this as kind of a module, so people can use. And this module, the idea is that you can use this module to encode dialogue history or turns. And we need to take care of these three things. Of course, for instance, the first one is provide pre-trained encoders. This is already solved by Hugging Face Hub, so it's okay. But it's the second one, allow pre-training of new encoder. This is really important. So we can pre-train new encoders, will be nice. And also to have an easy way to fine-tune. So it means that we need to define a common abstraction or a common interframe sort from the previous example, for instance. And we can see that from the previous example, what we have is, for instance, we should read first the data, so convert it to an object, and then to actually load it, right? And here this will get the pairs, the things that we want to get closer or far apart. And depending on this change that we use here, switching these boxes here, we can get the different models. Let's say, I can get the dialogue history here with special tokens, the next response, or simply the previous turn, the next turn, or maybe the turn, corrupted turn, history, corrupted history, and we can change these things to simulate different architectures or different papers even. And then we pass this, we get the encodings of each one of the tokens. We apply some pooling. Then now we have finally our vector that represents the input. And then we have the target loss that will have here the notion of distance in this space, which means the similarity, right? The loss will take care of actually moving these points in the space, right? And if maybe we can have multiple target loss to move the space and make them get closer, having different criteria, not only just one. So it means that for each one of these boxes, we need somehow to provide components. For some of these already are out there, like datasets, we can start datasets, for instance, right? Or for the token encoders, any of the models, like transformer models. And the actual architecture not architecture, but the actual components of the module of K embeddings per trainer, what you can import from K embeddings per training is basically a data submodule that takes care of data readers, data sets, and samplers for dialogues, for instance. Like, let's say you have a sliding window dialog that, given a dialog data set, it will provide the pairs like turn and next turn, right, for instance. Or, as you will see in a few slides, it's also nice to have a variable size batch samplers, given the nature of dialogue that it's shorter conversations suddenly go up like these. Dialogues sometimes have this kind of shape. And then we have the losses component that contains all the losses. We already implemented 10 of what we could find on papers related to dialogues and others to just representation learning. And we have decided to have a base loss and base contrastive loss that all losses must inherit, because we have there some common things, like for instance, for contrastive loss, we take care of distributing the batches across computing, because batch size is really important in contrastive loss, because it means how many points you're moving each time you backpropagate, right, in the space. So we need to take care of this also. And for instance, we have, of course, the hard negative sampling. All the losses that we saw in the papers are already there. And then we have the evaluation component that contains some, like, for instance, few-shot classification evaluator that uses a prototypical network that will be explained by David in a few slides. And some utility, just like cache or distributed. This is optional, but you can have a decorator in a function and it will hash the input, and you can say that how to hash it, and then you will dump to disk wherever it's coming as an output. But also it's optional because we know that the cache can be dangerous sometimes. If you change something, you assume that the output will be updated, but it's still getting from the cache, so you need to be careful. And then we have finally the trainer that takes care of the training. It means that it takes care of checkpointing, the logging, user weight and bias, the resuming computation in case of crash. It will restore the session in weight and bias, etc. It will, if in distributed computing, it will store the checkpoint of each one of the processes, the optimizers, etc. And well, finally, we have a way to pre-train embeddings, but we need to somehow measure the quality of these embeddings. So it means that we need to evaluate the quality, but in the context of task-oriented dialogues. One way to do this, that's what in the papers that I was mentioning the previous they do. Well, the simple thing is to actually evaluate the embeddings on downstream tasks, like intent classification, domain classification, dialog classification, response selection, etc. But not just in any way, right? Because we want not to we don't want to evaluate the quality of models that take care of this using the embeddings. We want to know the quality of the embeddings itself. So basically, the method that we'll use is prototypical network probing and few-shot fine-tuning that will be explained by David now.
Okay. So hi, everyone. Quickly check. Okay. Yeah. So basically, let's start with prototypical network. So here the goal is really to evaluate the embeddings themselves. So basically, we take our frozen embedding model as is. So for example, our word model. And this is a few-shot evaluation. So basically, for example, in the case of intent classification, we have, for example, 3 examples, or here 2 examples, per different intent category. We embed them, all of them, basically in the space. And then if we have a new sample X here in this case, and we want to say, or classify this example, we first calculate the centroids of all the different embeddings we have, and just take the closest centroid. So basically here, X would correspond to the orange class. And basically here, the goal of that is basically really to evaluate how good are these embeddings as is for different downstream tasks. Then the second type of evaluation we did is probing. Here basically we still freeze our embedding model, but add one linear layer on top, which is then trained on the full data set, for example, again for intent classification. And with that we kind of try to answer the questions, how easily can we transform our embeddings with just a linear projection for a new task. And the third type of evaluation is few-shot fine-tuning. Here we basically fine-tune our full embedding model and train also again just on n examples per class. And here the goal is to say basically how easily can we transform our full embedding models with just a very small amount of data to a new task. So basically how general is the general representation of the whole model. Then for the data sets we actually used for the evaluation on downstream tasks for intent classification, we used a few standard data sets, which are basically just single utterances where you want to classify the intent. For example, bank 77 is from banking conversations, so things like what is the balance of my account, or SNPs is a data set from home automation, so something like turn on my lamp in my living room or things like that. Then the next task is dialog level response selection. So this is basically the task. You have a set of candidate responses for a possible user turn, and basically just want, based on the candidate responses, select the one that's most appropriate. So here we use a data set for DSTC7, which are conversations from a Ubuntu help forum. And then finally, for domain and dialog classification, so domain, just the domain of the dialog act, like the general act of conversation, we also use the multi-words data set that was mentioned multiple times already. So then basically here's some results. So here we focused on basically the similarity-based prototypical network approaches. So first, intent classification and response selection. So here the numbers are basically on 1 and 5 shot evaluation for intent selection, and for response selection we calculate accuracy at 1, at 3, and 10. So basically, if from our top 100 candidates is the correct one in the top 1, top 3, or top 10. And basically the first result is here just taking the standard BERT model without any additional training. So then the first row is basically our kind of small-scale replication of this DSE approach. So basically just having this next response selection training with this hard negative sampling loss. And basically see quite good improvements on top of doing no additional training on BERT. Just to show you how this then basically also implemented in our framework, you basically have, where's the pointer? Yeah. This is just the sliding window dialog dataset, which basically constructs the dataset and then just use the corresponding loss, and you are ready to go to train the model on your data. Then one important point, as Sergio already mentioned, for these kind of losses is actually also the batch size. So basically this tells you how many, as he said, how many points you are moving in the space, and you here see a clear improvement with larger batch sizes, but which also becomes more complex since you need more GPU memory to basically load these things at the same time. And that's also really important to have them at the same time in the GPU, and you can't do things like gradient accumulation. Maybe one also interesting difference between DSE and the original Todbert paper was also that in Todbert they used a batch size of around 32 and for DSE around 400, which was also one of the main reasons they got quite good improvements. So then one thing we also tried to basically make more use of the memory, as Sergio also already mentioned, was this variable size batch size sampler, which basically just says if our sequence length in the current batch are shorter, we just take more samples. And here this also shows we get some improvements on response selection, but here, so mainly helps for response selection, because this is basically also the main task it's trained on. And then again here, you can basically just take the corresponding sampler and you're ready to go. Then another thing we tried was this denoising autoencoder loss. Here the idea is basically to just have a separate autoregressive decoder that basically takes as input via cross attention our embedding and regenerates the original sequence, where you might have then also some additional corruption on the input. This helps a lot basically to have or learn some more semantic representation. So for example, specific words or specific slots in the input. And this also helps a lot for intent classification with some degradation for response selection. And again, this is just in the framework, adding this one loss. And then another thing we tried was basically when sampling the data to use unique dialogs, basically just sample from the same dialog, and also to sample unique labels, so basically avoid that in the negatives we have examples with the same intent. So because from the response selection this might hurt the performance if you basically take samples with the same intent as negative. But here the results are not so conclusive, I would say, yet. So once again, just a simple sampler you can add in our framework. Okay, another ablation experiment we did, or what was kind of interesting in the related work, is that Todbert still trained on this additional mass language modeling loss, which wasn't really done in other papers. So basically wants to investigate, does it really have an effect? Kind of this ablation was also missing from their paper. And here we see quite a strong trend that basically adding the mass language modeling loss gives on all evaluation tasks some clear improvement. So basically this is also something that motivated us that we should basically integrate this in our pre-training framework, which is not yet done yet. But maybe also this effect becomes again smaller if we increase the batch sizes and then the training becomes more stable. Then again, we did basically for the evaluations, we basically run them on all the different baselines. Here's basically just one excerpt of a basically large Google Sheets table we have, comparing all of them. And basically also one conclusion is that these GTR T5 models really work well, since they were really trained on a lot of data and also use these T5 checkpoints, which were trained on more data than BERT as a baseline. So this was also one motivation that these were probably a good starting point or inspiration for the future work. So one additional experiment we now started to work on basically last week or 2 weeks ago was adding then more supervision to the training of the embeddings, because before basically focus on response selection loss, but you might want to use some additional labels from task-oriented dialog data sets, like for example the intent labels you have. And so here everything we added was basically use a contrastive loss with intent labels, so basically saying utterances or terms with the same intent should be close to each other, and with different intents you would want to push them far away. And basically as expected kind of, we get a clear improvement on the intent classification task, but some degradation on the response selection task. And basically, I would say this is actually quite expected. So this brings us kind of back to the original question, what kind of similarity do we actually want to encode? So for example, if you look here at the example, where can I get sushi in Le Mans? So when you say basically that your similarity measure should be intent, then you would say that basically it should be close, or the representation should be close to the utterance. Where can I get ramen in Le Mans? Because in both cases, the intent is kind of find this restaurant in this category. But at the same time, if we train basically actually for next utterance prediction, something similar would be something like the sentence, Tokyo sushi is a popular place for sushi, since this would be an adequate system response for the user question. But at the same time, you wouldn't say that basically the representation of these two sentences should be the same, because there's basically no relation between them. But if we train basically with the losses we have, this is actually what we kind of get. So this brings us kind of to the point that actually we would want to have, want to have different representations per task. So some kind of representation that's suitable for intent classification, some representation that is suitable for next utterance prediction, and then ideally this brings us maybe to representation that is actually useful for clustering for our use case. So of basically building these dialog structure states. And basically one approach to do this would be to add a prompt as prefix to the model. So something like represent the user utterance for intent classification. There's some related work that did this for this more classic semantic similarity and information retrieval the task. But basically their model doesn't really work well for dialog tasks, because they basically didn't train on any of this and basically don't have any training data for these specific tasks. So even with their model, we get some degradation, for example, for intent classification. So this brings me to the next steps for basically dialog embeddings and turn embeddings. First, we want, basically based on the experiments, we want to support these token level auxiliary losses like masked language modeling. Then in general, we want to scale up the training, then takes longer, so using large batch sizes, more data. So for example, based on this unified dialog studio framework, we already collected a data set with 12 million total utterances, which is more than 10 times the data we use till now. And also we definitely want to investigate further this to instructed embedding models, since basically we think this is a really promising direction to get more nuanced embeddings that you can basically adapt to what you actually want to do downstream. And finally, we also then looked at spoken dialog embeddings, and there Bruno will tell you something about it.
Thank you, David. So hello everyone, I'm Bruno Melicio, and I'm here to answer David's question. And basically what they have shown so far is that they can do all these tasks with text embeddings, but we also might want to work with speech. And usually this is done through ASR, which converts the speech to text, but this might introduce errors. So why not extract embeddings directly from speech? And similarly, if you think about the evaluation on dialogue-related tasks, most of them are performed in text-based models. So for instance, if we want to classify intent, this usually you start with a text, send it to a text encoder, and then obtain text embeddings from which you can do the classification. But if you want to use speech, you can actually send it through an ASR that converts it to text, and then the process repeats. But we can, as I've mentioned, we can actually do this directly from speech and now obtain speech embeddings instead of text embeddings. But we might not need to limit ourselves to one modality. We can actually use information from both text and speech, from which I will refer throughout the presentation as joint speech-text models. And in this case, the speech embedding would have information both from speech and text, and the text embedding would have information from text and also from speech. So here, my goal was basically to use embeddings from joint speech-text models for intent classification on the slurp dataset. The model that I have been using is called SpeechT5, the base version of it, and there are 3 main checkpoints that were provided. One is the self-supervised learning, which was basically pre-trained with a lot of text and audio. Then there is an ASR version, which is also pre-trained with text and audio, but then further fine-tuned for ASR task. And there is a third one, which is the same, but later fine-tuned for text-to-speech task. Here, if we look into the architecture, we will see that it's an encoder and decoder model. Whereas because we want to get the embeddings, we should focus only on the encoder part, which is jointly pre-trained with text and audio. And here it's worth pointing out that if you see the input, when we send speech, this is sent separately through a speech encoder prenet. And then when we send text, it's also sent separately through a text encoder prenet. And if you look closely into what joint here means, basically, it doesn't mean that we want to get a single embedding that represents speech and text. No, instead, what we want is for an audio and the corresponding text, obtain 2 embeddings which should be close in some latent space. So basically what I have been doing with the slurp dataset, so if I take an audio, then I send it to SpeechT5, and in this case we obtain frame-wise embeddings, meaning that for every frame of the audio, I obtain a 768-dimensional vector. But as it was mentioned before, we actually want to represent individual turns. So we learn a weight matrix that learns to basically select parts of this frame-wise embedding and convert it into a single vector which describes the individual turn. And then we can use this for the task of intent classification. Similarly, if I take text from the slurp dataset and send it through SpeechT5, we obtain token-wise embeddings, which we can also learn another weight matrix and then represent this as a turn embedding that can then be used for intent classification. So based on this, I've done a few experiments. The first one consists in comparing text joint embeddings with text-only embeddings, meaning if I send text to SpeechT5, I will obtain these joint text embeddings from this joint model. And how does it compare with obtaining text embeddings with a text encoder only model? And here to show some results, first I showed the baseline, which is reported in the original slurp paper, where they achieve 84.84% in intent classification. And then if I take the self-supervised learning version of SpeechT5, this actually underperforms. It achieves only 57.97. But then if I take the version which was further fine-tuned for text-to-speech, it achieves 86.62, which is more than the baseline. But we also look into other methods in the literature, and to our knowledge, this speech brain recipe is the one achieving the most accuracy, 87.28, but it was actually trained on slurp, which is different from the others, which were actually pre-trained in something else, and then only these last layers were fine-tuned for intent classification on slurp. Moving on, other experiments that we did was to also compare audio joint embeddings with audio only embeddings, meaning if I take speech and obtain a representation from SpeechT5, how does it compare with obtaining speech representations from a speech-only encoder? Also, because SpeechT5 is jointly pre-training text and audio, then it means that the representations or the embeddings from speech and text should be similar, but does that also mean that they will have similar performance in some task? So basically, if I take the text embeddings from SpeechT5, how does it compare from the speech embeddings also from SpeechT5 in intent classification? So first, reporting the results from the baseline on the original slurp paper. Here we see when in the slurp paper they used audio, they actually first sent it through an ASR to obtain text, and only then did the classification, which achieved 78.33%. Then if I take the SpeechT5 self-supervised learning version, this actually underperforms, and here it's using input directly from speech. It achieves only 41%. But if I take the other version, which was fine-tuned for ASR, then this achieves 87.02, which is a massive improvement. And then we also look into other methods in the literature. There is one reported by ASP.NET, which is Hubert-based, and it achieves 86.3. And there is another one from SpeechBrain, also Hubert-based, that achieves 87.54. So making some sense out of these numbers, basically if we take the best text method and the best speech method, we observed that for intent classification on Slurp, the speech-based embeddings performed slightly better. It could be that there is some more information on speech, but this needs further research for us to give conclusions on that. And also, jointly pre-training on text and audio and then fine-tuning on a specific task improves the performance. For example, we've seen that using just the self-supervised version of SpeechT5 from text was 57.97, but if it was the fine-tuned with ASR, then it achieves 86.62, and the same for speech, 41.02, and then 87.02, so we see this improvement here. But this is just one part of the project. In the future, we tend to explore other models like SAMU XLSR, and also use other data sets and tasks. And in this case, what I've shown is that we can actually use speech embeddings without the need of ASR, but maybe if the ASR-based models have a longer context, they might actually achieve better performance, which is what my colleague Alex will continue.
Thank you, Bruno, for the introduction. Hi, I'm Alex, and I will cover now the ASR part of this scheme. So basically, normal casual ASR works per utterance level. So we are probably maybe missing some context from long conversational, and this can maybe help us to obtain better results. So we designed and analyzed architecture where we basically keep the context and encode and decode conditioned by that. This can help us to dynamically adapt acoustic model to the channel and speaker information, and adapt language model to the semantic content and topic of the conversation. So for the data, we used Fisher conversational speech corpus, which has like 11,000 conversations that range around 10 minutes of length and are about 40 topics. However, there is no official splitting, so we have to do it by ourselves. So we created two training sets, the smaller one for all our experiments that has 500 hours, and the bigger one containing 1,500 hours. Those only contain 34 topics, and we created a def and test set that contains another 6 topics to see how it goes. We also did some analysis on the speech version of Multivoice to show if we are able to improve there. So basically, now I will just, since we introduced new splits, I will now cover how we built our baselines since we didn't have any. We started with the attention-based encoder-decoder with the ESPNet recipe. We get 15.4 word error rate. However, we wanted to do some analysis if we are able to train our models more efficiently and if we are able to scale our problems and obtain better results. So here, fire states for the part of the model that are trained, and the snowflake stands for the parts of the model that are being frozen. So here you can see that encoder and decoder stays frozen, just the adapters are trained. And here you can see the number of trainable parameters and the and the word error rate. So as you may see, the best results were obtained after also tuning the encoder parts, since the XLSR didn't see any part of the Fisher dataset, and the best results were obtaining even after introducing additional CTC loss. If we scale our problem a little bit more, add all of the data, this 1,500 hours, and add additional parameters to the encoder and decoder, we are able to get additional 4% improvement. So, motivated by the initial experiments with the casual language modeling that will be later introduced by Santosh, we tried to also introduce the context awareness to the encoder part of our model. So this is the model from the previous slides, our baseline. And now we take decoder frozen as it was, encoder and decoder frozen as it was, and just add here attention pooling to pool our hidden states to obtain single summary vector, then append it and update our context vector and prepend it to the hidden states and send it to the decoder. However, as you may see, these are two less parameters added here, and the model was not able to learn anything. The performance degraded. So our next trial was to add here cross-attention block and basically prepend all previous context vectors. So here we are able to attend. We are able to attend to all of the previous utterances in given conversation. With this, we are able to get some improvements in the terms of word error rate 0.02, which is nothing. And this doesn't show anything that would significant results. So we tried to scale our problem a bit more with this. Basically, as you may see, this is the same architecture. Just you take the encoder, and in every layer of the in every transformer block, you introduce the attention pooling and the cross-attention block. By doing this, you have context for each layer of the encoder, and you can do the same thing for the decoder. But here is a bit more difficult, since we are not able to adapt to the, we cannot adapt to the current context vector, so we have to take the previous one. However, we've seen some improvements in single conversation during the training, but after some steps, the model converged to just mess. So we further revisited the initialization of the model, did some experiments. However, we are still not able to get anything significant from the model. We get some improvements, but after just few steps. So we have to probably revisit the batching strategy, which now goes sequentially through the utterances in batch of conversation, and we should do it somehow more randomly, and that may give us the results we want. So that's all from the embedding part. We showed you the strong toolkit we built, where we basically can pre-train models with just few lines of code. We compared several architectures for the embeddings and intent classifications and response prediction. We showed that we are able to get similar performance from the speech and text, and we suggested that we don't even need to do ASR for our spoken dialog system, and designed and analyzed context awareness ASR models. So that's it. If you have now any questions, we would be happy to answer you. This is just the embeddings part. We'll continue later.
Questions from anyone? No question for you? All right, looks like there are no questions. We should proceed. By the way, who's watching online? Is anyone watching the chat? You are? Okay. So far, okay.
Hi, I'm Andrzej Platek, and I would like to build a bridge between the first part of the presentation and the second one. In the first part, there were two toolkits for the dialog embeddings, the data, but also the spoken embeddings. But on the downstream task descriptions, I will build a base for the next part, which will be much more challenging to follow because it's completely new. And let's get started. So we will basically just recap what the basic dialog research was doing in last 20 years and what kind of representation it used. And at the end, we will see that maybe it's not enough and we can do something better. So what we have here is a very simple dialog, right? It's task-oriented dialog where, as traditionally, user wants some restaurant. And like the system provides some information that there is some cheap restaurant. And the meaning of this conversation, or each turn, which is separated by the dotted lines, is represented in dialog act items. This inform is dialog type, this is the slot name, and this is the value of the slot. Similarly for the user and for the system. And the guys, Sergio and David, talk about some evaluation that, for example, the downstream task could be to track what user said. And at the third turn, if you aggregate all the annotation for the user said that it wants cheap restaurant, it requested like what kind of cuisine it has, and then the user wants to like finish the conversation. It says goodbye. So our topic is a dialog structure. So how this research, how this representation could lead to the dialog structure. So one way to how to look at it is if you have some conversations or already recorded, and you ask some specific question, the conversation will get clustered, right? So like if you asked what the user wanted at the end of the dialogue, and the answer will be like cheap restaurant, he requested a cuisine, and at the end of the dialogue, there will be several dialogues like that, and the dialogue will naturally cluster. If you ask other question, like what the system attempted to do, what kind of action it used at the end of the dialogue, again, the dialogue will cluster according to the labels. One notion which I would like to stress, we are not interested only like clustering the whole dialogues, but all the sub-dialogues, right? So if we look at the end of the second turn, instead of the whole conversation, this is also like a conversation for us, and we will use it like that in the second part. Okay. So I want to recap a little bit here, and I would like to wake you up before the coffee break. So there are two good things. You will wake up here, and you will wake up with the coffee. So there were some, like Sergio and David presented the accuracy on response selection. Response selection is if you like monitor the state using the dialog act items, and then you select a response, you measure the accuracy. And there was like this number, like 1/3. Does somebody knows what it means? Like, yes, like so, like there's some nodding. So I will explain it. So it's like you take first you take some set of responses, for example 100. You include the one you predicted, and you report like accuracy, like a hit, if it's in top 3. And we reported top 1, top 3, and top 10, if I remember correctly. And why is it important? Because if you perform well here, you can cluster based on the embeddings or based on the annotation you predict how the system replies, right? If you like can do this task and have these annotations, you can also ask like what are the most frequent system actions for the sub-dialog, etc. So this is how it links the downstream task to the clustering. And similarly, dialog state tracking. It tracks all the annotation I showed in the previous example, and there is like the accuracy on joint goal accuracy. Again, it really matches all the, like, if you like concatenate all the annotations, it has to be exact hit to have like, to be very accurate, to have like 100%. And similarly, you can track belief state, etc. So we were thinking how to use these downstream tasks and these annotations for dialog clustering, and we realized some like that something is not that useful. For example, you may think like name entity recognition. It's kind of similar, right? But for example, if you track something like cheap restaurant, the cheap will never be like tagged by name entity recognition. So it's kind of similar, but not always the same. And now we are moving towards like I would say breakthrough. Like after like several decades of research, somebody asked, okay, we don't want to look at the conversation structure like what was said up to this point, but they try to look at the time dimension, and they ask the question, what was mostly discussed in the conversation? What was talked about? And I will introduce this notion where basically the paper, the structure extraction in task-oriented dialogs in loss clustering, introduce a vector. And it's like sparse vector, where at the beginning of the conversation, you have zeros. And you basically count how many times the slot was mentioned. And I will introduce examples later, so let's get started. So I will present 3 short conversations, and I will read them first. I want a cheap restaurant, user said. There is only a lot of cheap restaurants in the countryside. I want an expensive restaurant in the countryside. Sorry, there is no such restaurant. I want expensive restaurants outside of the city center. There is a nice restaurant, Vojty, in Libeň. It's near to Vojta Hudeček, which I say hi to. So, do you have any idea, like, what happened? Why the user didn't get the first restaurant? And it has like this vector. But the problem was, like, there was no such restaurant in the database, right? So the system needs to like offer something else. And what's here? These are the vector. Like this is the slot name, and the price range was talked 3 times in this user turns, like 1, 2, 3. The place in was talked 2 times, countryside and city center. So here, I want to show that on 3 examples, you will get the same representation, but for example, this representation cannot differentiate by the reasons why the like, it answers the question what was talked about, but it's not perfect yet. So again, I want to go to an expensive restaurant this time. Vojty downtown, there is the restaurant you know already. And there is like, user wants something else, right? Less expensive in the city center. But now like the user like wants completely something else. And there is like 1 restaurant like near my home, right? So here, the problem is that the user changed the mind on its own, and like it happens. The system did nothing wrong, but still, it took like 3 turns to get user satisfied. They talk about the price range 3 times. Sorry, I have a typo. They talk about the place in 2 times, and you can compare it with the original vector and notice my typo actually here. Sorry for that. So the last example is user said, I want a cheap restaurant, and ISR people knows this example. Sorry, I don't understand. So at the end, the system understood and picked the restaurants by me. Again, this is the same vector, but the reasons why we get to the same vector are completely different, right? Like the first one, it took 3 turns because there was no entry in the database. The second one, the user changed of its mind, and we as the system cannot influence that. And the last one, hypothetically, this was because of the, let's say, ASR error. So to conclude, we will present some dialog structure at the end, in the second part. And now I hope you are still awake and you will be ready for the second part. Thank you.
Hello, I'm Miroslav, and I will tell you something about similarity scoring, which we thought will be some of the essential parts of our groups, and how it came that it was a one-man show for a brief period of time. So we were inspired by some human parallel, and we wanted this similarity score to represent the way how people handle the calls, and usually they do that in the call centers in a way that they know a lot of calls that happened in the past. If they are in the middle of some conversation, they know what usually happened in the past calls and what happened afterwards. So they have like the full training set in their mind. And we wanted to have such a metric to evaluate our clustering methods and so on. We decomposed that thing into two parts. One of it was dialogue history alignment. So like if I am in some point in the conversation, I'm able to find the most similar dialogue subparts in my training data, and then to define some metric which helps us select the next action. I have illustration here. We did some very naive implementation using vector database, FIS, and we tested several of the embeddings that were mentioned before, like DSE or Toolkit, and some approaches to address the dialogue history. And it works like that. You have a training set of dialogues, and you have some partial dialogue in inference time, and you want to select next best response from system or user. So dialogue history alignment helps you to align these dialogues so that you know which states in the training dialogues resemble the point you are at right now. And then you use some metric to select the next action, maybe just by the length of the road till the final state, or maybe by some other attributes of the path that you are able to retrieve from the data, right? So we saw there a few challenges that just simply using these embeddings, it sometimes failed to distinguish whether we are user or system. It couldn't find some condition steps or coherence in actions. For example, finding a train from Chicago to London is not a problem, and it's not grounded in a real world because there's no such train connection and so on. There may be also emotion-related shifts where the customer gets angry or something like that, which is hard to see from just the textual data. We had this metric, but it was sort of hard to evaluate it. Common things to use are BLEU score or I/N to discover the recall. It sort of worked on the multivos. It was worse than their baselines, of course, because we didn't use all the information. But we were also arguing a lot about the evaluation, whether these metrics are actually good, because if you, for example, imagine some ending of the conversation when a system can say, yes, that's all, thank you for interaction with me, bye. Or he may ask, do you need something else? There's no matching there in BLEU score, and it might not even get selected in 1/n, but it's a like meaningful continuation of the sentence. So we saw that on multivos it sort of worked, even this very, very naive approach, but of course it didn't maintain the coherence and the other issues mentioned before. But if we tried that on some proprietary data or on Alomedia's data set, it failed immensely, maybe because there's need for further pre-processing of the data or something else, but we all got really, really excited about the slot-based approach. We focused on that, and we have seen that the dialogue history part itself is so demanding field that we need to focus more in there. So the whole similarity score thing is left for the further investigation after the workshop, and that's why it has been only brief one-man show. And I will hand over word to Martin Vania.
Hello everyone, my name is Martin, and it is my pleasure to introduce the pinnacle of our talk, and that is the dialogue structure discovery. That is the part that is in the middle of everything. Everything is connected to that one. And even though I'm going to give the introduction, I will immediately jump to evaluation and then leave to others to elaborate on the dialogue structure discovery, actually. So first of all, I will return to the motivation. As Peter already tackled, the contact centers are harnessing a huge amount of data, yet there is almost no possibility to leverage the data for their own benefit. And the reason for that is we've been telling to companies, you need to transcribe the data, you need to put it in a storage where you can search in the data that is going to help you to automatize your quality assurance process. That's not the truth. It's so difficult to extract any information by just full text search. It's not even possible to do that with actual classification. That's not enough for giving some relevant information. And so the proposal is we need a structured approach. We need something that goes from top to bottom, and that is difficult. And for that, we need to label the conversation. We need to label the pieces of conversations, and we need to have some notion of transition between different parts of the conversation. And that goes for the structure discovery. And yeah, for being able to label pieces of conversations, there are many core methods. And of course, some of the simplest ones, and that's the baseline I will talk about, is just get the embeddings and cluster the embeddings, and you will get some sort of labeling, and then you can see how are you moving through the states. Or as my follower will talk about, we have tried also prompting some large language models, give me the labeling from there. And there are others like generative models or wave-to-vec inspired method, or the slot-based clustering. You already heard some of it. Now, what I'm going to talk about mostly is going to be how to evaluate this, because unless you can evaluate, you are blind. You cannot say how well are you performing. So the idea is that if I have some sort of a labeling, and I'm now talking about a labeling that is coming from your golden labels, something that is annotated in your data, I should be able to tell how well I am approximating that labeling. And for that, we are using two methods, and there is a reason why we are using two. I will later on talk about that. One of them is rand index. Basically, you are choosing the pairs of your data points and take a look whether they belong in one clustering to the same class as well as in the other clustering, or whether you are having this like, does it work? I do not see the point. Over there. So when you take a look at this, the color here, the yellow color shows one clustering and the pink color shows the other clustering, while the circles one cluster in one clustering, second cluster in first clustering, and then you have the circles which are denoting how the second clustering method works. Now, if you take a look at the green lines, those are connecting positive examples when in one clustering and in second clustering, I'm in the same cluster. While here, in both clusterings, I'm in different clusters. So that is what rand index leverages and then divides of how many possibilities are there choosing a pair of data points. The second one, the mutual information, works slightly differently, just looking at the overlaps between the clusters. So how many points are in one clustering and how many points are in the second clustering, and then how many overlap. And that gives you some notion of similarity of those clusterings. Now, these random index and mutual information does not account on how well I would perform if I would just choose randomly. So that's why our standard method is to use something called adjusted rand index or adjusted mutual information, and that is you subtract expected value of random clustering, which forces your numbers to go between -1 and 1. As close to 1 you are, the better the clustering is. If you are at 1, your both clusterings are exactly the same. So the higher number, the better. And I will not talk about that method any further. You can look it up. We are using the scikit-learn package for that. So it's a common thing to use. Now, what we are actually going to take as a golden label. So Ondřej already introduced the state vector tracking. And this is something that we have taken from this article. Is structure extraction in task-oriented dialogs. And we are not actually doing the method they are using for this unsupervised detection, but what we are taking is the baseline of how to evaluate. So first of all, you have initial vector, which tells you, I haven't detected yet any slots, so I'm in a 0 state. That's a beginning of every conversation. And then when something is mentioned in your call, doesn't really work. So something is mentioned, I increase the value of the slots because they were mentioned, and I'm propagating this throughout the conversation. So I'm getting these types of vectors. And what I'm doing here, that's the most important one, I'm assigning a label to every type, every unique combination that I have in that vector, I assign one unique label. And therefore I have some labeling, which I can use as a labels of the states where I am in the conversations. And so what I have now is golden labels, and I can use, for instance, the k-means, take the embeddings, use the k-means, and compare the labeling that you get. Now, interestingly, in this article, they have created some method which is somewhat performing, but they have also done the baseline that I wanted to reproduce. And if you take a look at the numbers, those are very, very poor. And one very interesting thing is that the rand index compared to the mutual information is about order of magnitude lower. It's near 0. It's like telling, hey, this is something the same as random clustering, right? So that is actually quite weird. Now, I had to dig a little bit in the method, how they did it for the baseline. And the issue here is that every domain of the multi-was on which we did all of the evaluations was treated separately. And on every domain, they have taken as an embedding of the conversation just single utterance pair. Yet what they are actually trying to cluster is in the space of all possible states of the whole conversation. Now, it is kind of unfair because if you are, if you are trying to guess what is supposed to be here in the conversation, is somewhere in the middle of the conversation, if you have 0 context in your text, you cannot create an embedding that would distinguish. So that's the reason why the numbers are so low. And so we tried to approach it slightly differently. So I know that I have 5 domains, and we did the evaluation, same as in the article, only on the separate domains. And there are 2 possibilities. Either I'm clustering only the changes in the state, and then I have very small number of clusters. Here you can see the number of slots that are labeled in the data, so I can use that one. And then I'm reconstructing the vector in the very same way as is been done in the golden labels. Or I'm doing another thing. I take all the combinations of states that I expect to see in the data, and I cluster over embeddings which have all of that context. Now, interestingly, the first one that I tried, and I tried it for multiple models, are showing much better numbers. In some cases, for DSE but large, it's actually accounting for more than half of what they achieved with slot tracking method. And it is quite interesting. So as a baseline, these numbers should be actually more accurate. But more interestingly, I have evaluated how this behaves if I take, for instance, Todbert, and I add to every single embedding of every single turn more context from on the left side. And you can see that it's increasing, and basically for some domains it's really beating up the numbers. And that is quite nice because I'm now clustering over all of the possible states in that conversation. Not just individual changes, but all of the possible states, meaning that the embeddings are showing that they are actually encoding the history well. And out of lack of my knowledge how the DSE should be used, I tried that actually on DSE as well. And frankly, I was surprised because it works even better than Todbert, even though it's not trained that way. which is kind of interesting. And here you can see like I'm getting near 0.3, near 30%, which considering that the baseline or the target they had in the original article was about 50 or less than 50, around 40, it's actually quite a good number if I'm doing just only k-means of the embeddings. So as a conclusion of the evaluation, the baseline that we should be targeting if we are comparing ourselves to this state tracking would be these numbers in AMI. And as you can see, these numbers for ARR are actually still very small. And those are much better if you are going with a real state tracking. The reason for that is, and I had to really take a look at that, is that if you take a state tracking vector, you know that at the beginning of the conversation there are only very few combinations that you can have. Meaning every conversation you have in your dataset will go through some of these small amount of states. But if you are going further, the amount of possible combinations of your states is exploding. It's a geometrical thing. How many slots I have, that is the combination that I can get to. So most of the end states are actually quite underrepresented. And the skewing is actually what you are seeing here in the numbers, because the RAND index actually prefers much equal-sized clusters, while the mutual information prefers skewed size, where you have large clusters and smaller clusters and very, very sparse clustering. And that is basically what we have discovered for our baseline, and then I will ask Gabor to pick up here with the prompting methods.
Okay, thank you. So following what Martin started, one of the core methods that we were using is related to prompting large language models. And for that, we tried several methods. First one was in the very beginning of the workshop, the instructor embedding, which was trained for multiple classes. It was very useful, but it was very slow. So at the early stage, we had to discard it. And the next one was the Falcon 40 billion instructor. It was also very good, but in the middle of my research, Llama 2 was released, and I tried also the 7 billion version and the 70 billion version and the 7 billion version. Chat and the human feedback based seem to be very friendly, very easy to use. And what we can see here, we have the default prompt request. I didn't really follow that, so we moved to another approach. So it's not really following the structure of the prompt, but here what we can see, first I provided a dialog which is just a pair from a user and a system. So first system user utterance pairs, and the interesting thing here is it's exactly the same what was mentioned in the paper. And what I forced the model for to predict type, which can be either intent or slot, and for each of them we force the model to predict the intent type and value, so intent name and intent value. And after that, we had the proper JSON format. The whole dataset have been evaluated. The dataset was multi was 2.1, not 2.2. And here is an example how I proceeded, how I went to the problem. So on the highlighted orange utterance pairs, you can see what I gave as an example to the model, and we can already notice what is the problem with the large language models. So here, what's interesting, the sports was given here as an intent name, but the model somehow hallucinated extra informations like football, Newcastle, St. James's Park. And what is really interesting, these are connected to each other. So football is a sport. Newcastle is a football club in the English Premier League. And its stadium, surprise or not, it's St. James's Park. So there is a nice track of hallucinations. And after that, there is still plenty of work left. So I already covered what type of hallucinations we have. And we already seen that the quantization drop we can experience with the large language models. However, with using a larger one, it's less painful if we use the quantized model. And also, we should fine-tune the model to avoid such huge amount of hallucinations. And moving towards to the state tracking vector reconstructions. we wanted to extract informations. That's why I used this kind of prompt. So if I move back to the, what? I should go to the other direction. Sorry. No, sorry, this way. It wasn't straightforward. Sorry, so here we are not using the values, just the intent names. And this is very important. So here, in the rand index, in the mutual information scores, we can see from the multiples data set, only the hotel was evaluated, and we can see already the mutual information is pretty high. But as Martin mentioned, the rand index was really low. So this is expected. A lot of work left in this field to follow the instruction, prompting the models. So technically, this is it from my side, and I'm going to pass the word to Santosh.
Thank you, Gabor. Okay, I'm going to talk about generative models for learning dialogue representation. And I will tell you how it's kind of related to what we were doing and how we can use the framework of generative models to actually model the dialogue representations. So here our goal is basically adapt some pre-trained language model to a newer domain like conversations without requiring to retrain all the parameters. And the application of this would be language model for task-oriented dialogue system or adapting the language model for long context ASR. And we also want the model to give us embeddings for the utterances, and these embeddings should take the context of the conversation into account. So we would like context-aware embeddings. And once we have these embeddings, we can again evaluate these on several language understanding tasks, and that David and Sergio already presented in the part 1 of the presentation. And by having this framework, we can actually draw some theoretical relations to dynamic variational autoencoders and the contrast to predictive coding-based approaches. So the model is very straightforward. So we have, so X1, XT, XTs are the observed data, which are basically the utterances in the conversation. And LM is the pre-trained language model. And ST are the latent vectors that should represent the state of the conversation until the current time step. And the generative process goes like this. So we sample a state latent variable that should represent the state of the dialogue until at the time step. And then using the state and this latent vector and the language model, we would like to generate the next utterance token by token. But in reality, we have training data, which is basically conversations, and we would like to learn the best estimates of the latent variables given a frozen language model or given a pre-trained language model. And how do we train this model? The first strategy is, say we will have a context encoder that gives us the state vectors or the latent estimates of the latent variables, and then we can concatenate all the past state vectors. And this would be conditioned. So there will be some conditioning on the pre-trained language model, which acts as the decoder that will generate token by token in the current utterance. So in this case, what we have to observe is this language model is autoregressive. That is, it will produce token by token in the current utterance, and it does not see anything in the past. The only information that it gets from the past is through these latent vectors, which would summarize the past until the current state. And we train the model to maximize the likelihood of the data. Once the model is trained, we can just take the context encoder and pass the input text and then get the embeddings out of it. And we can use it as an embedding extractor that should be aware of the context. The other training strategy is we can even unfreeze the pre-trained language model. Let's say we want to update all the parameters. But usually the pre-trained language models are so strong that they can model the data so well that it can ignore the dependency on the state vectors. And for this, to avoid, we can do a slightly different kind of training. That is, we would like to maximize the mutual information that is in the state vectors, and that should help us predict the next token. So the objective function would be slightly modified, and we have something like a log likelihood ratio. So we would like to maximize the log likelihood of the data given the state vectors, but this one should be better than not using it. So this will ensure or enforce the model, the decoder or the pre-trained language model to depend on the embeddings from the context encoder. So these are the training strategies. And coming to the architecture, how we would realize it in practice is our LSTM is our encoder is an LSTM based. So LSTM is an encoder based model which takes the past utterance, gives us the state embedding, and then we have a cross attention block which acts as the conditioning, and this cross attention block could be added anywhere in the GPT layer where we have, like, let's say n blocks of self attention. So for the time being we can assume that this goes only at the nth block. Right. So this is the first architecture, and I will show you some baseline results. So even before showing the results of the suggested model. So for the baseline, we just took the out-of-the-box model, GPT-2, and we evaluated language model perplexity on Fisher conversational text. So Fisher is a conversation between two people, and the conversations are usually long, 10 minutes. It has around 200, 300 utterances. So they are quite long compared to standard text-based dialog sets. And the perplexity is actually computed per utterance, but then we accumulate the scores and average over the entire recording so that we can compare it across the models. And in this case, we have different models, small to large. These are the parameters. And the input to the model is only one utterance at a time. So it doesn't see any context of the conversation. And these are the perplexity results. Lower is better. And this is the time that is required to process each conversation. Since we have one conversation at a time, it is quite easy to process the whole data set. On the other hand, since the GPT-2 model is trained with very long inputs, up to 1024 tokens, we can make use of the whole context window and send the strings of 1024 tokens to the model, and then we can still compute the perplexity. This one gives us some improvement, but at the same time, it is actually much slower because it's based on transformer architecture, and the time complexity grows quadratically with the length of the input. So when we have longer input, it's more computationally expensive. So our goal is to operate at independent utterances, but at the same time give contextual information through the state encoders so that our forward pass is quite fast. So with the architecture one, so all of our experiments are done on the smaller version of GPT-2, and our encoder is based on LSTM with cross-attention block, and it just adds 7 million parameters. So here we have the baseline results. The snowflake indicates the model is frozen. Fire indicates the model is fine-tuned. So the first one is frozen, and we have perplexity on two different data sets, Multivos and Fisher. So one thing to observe, so there are few things to observe here. One thing is, the first one is when we fine-tune the GPT-2, again only on utterance level, it actually improves quite a lot. So which means the model is quite strong, and even without the context, it is able to adapt to the domain quite easily. And then by adding our encoder, which is LSTM and cross attention, and keeping the GPT frozen, we have again very nice improvements from the baseline one to here. And then by unfreezing all the parameters and, let's say, playing with different loss functions, again we see very nice improvements. But what is a little bit worrying here is the GPT-2 alone is capable of modeling the conversations without even looking into the context. And now the question is the LSTM encoder really capturing the state vectors that should help the GPT model, right? So the question that we are asking is the GPT strong enough to adapt to a new domain just because we have a cross-attention block? So what if we pass some random embeddings for every conversation without the LSTM block? Would it work? Would the cross-attention block would adapt to the random embeddings and improve? It seems so. Looks like even passing random embeddings through a cross-attention is actually good enough for the GPT to actually give us good improvements in perplexity. This is a kind of problem that is known in the area of variational autoencoders as posterior collapse, where even when you have samples from standard normal, which is your prior, the decoder is strong enough to ignore the dependency on the latent variable, but can still explain the data well. So we revisited the architecture, and this time we avoided the cross-attention block, and instead we prepend our embeddings directly into the hidden representations of the GPT-2. So again, in this case, for simplicity, we only prepend the embeddings in the final block. So the input is still embeddings, and here we will suddenly have prepended embeddings, which are the state vectors until the current time step, and then we have the output layer. So in this case, there are no trainable parameters in the decoder block. We have only the encoder block that is trained. And here are the results in this case. So again, we have the baseline, the frozen GPT, and the last line where we have, if you start with random embeddings, it actually gets worse, because as the conversation grows, we have we have more and more random embeddings that are prepended, and this actually negatively influences the performance. And now all the improvements that we see here, for example, using only the LSTM encoder or fine-tuning everything, is as a result of having a suitable state vectors from our encoder, and this is what the improvements are coming from. So let's say we have now the model. How do we even use it to visualize the conversations, right? So once we have retrained the model, we extract the latent vectors for test data. We know the sequence of utterances, so we know the sequence of the embeddings. We can do simple k-means clustering, and then take the centroids, and then pass the centroid to our generative model and say, okay, this is the centroid embedding that summarizes the state at the time of the conversation, and generate me most representative text of the cluster. And for the visualization part, I took Fisher test data, in which the subset of conversations are about the topic family values. So in this case, in the collection of Fisher data, so two people were connected and they were given a topic to talk about. So in this case, two people were talking about family values, and let's see what the visualization shows us. So this is the cluster we have, which we have discovered, and these are slightly pruned, so I don't show the transitions less than 0.1 probability. So what we can see is most of the conversations start either in cluster 6 or cluster 8. So around 77% of conversations start in cluster 6, and the red one shows where the conversations end. So from these red states, all the conversations end. So this is, at first glance, seems reasonable, because most of the conversations would go here and they would end, and there is some crazy dependency between the intermediate clusters. Let's see what the start of the conversation would represent. So I took the centroid embedding and asked the model to generate. Well, it generates something random. Well, in fact, it is not that random. What it is doing is it is generating very short utterances. And usually in the Fisher, the start of the conversation is basically a greeting. They would say, hi, hello. So essentially, our latent vector is capturing the length of the utterance. Let's say something in the middle. So again, the middle embeddings or the utterances are quite long. So I have two examples here. And something is about fruitful middle-class life, and something about your kid, most happier guys in the world. So something about, I don't know, middle-class life and kid could be related to the family, I hope. And let's see what the last cluster would represent. And again, this is a very long conversation and probably a result of hallucination. So this is only a visualization or the application of how we can use some generative model in the framework and try to visualize conversations or nodes in a clustering. We can even, so since we are in a fully generative model, we can even turn this into a prior by setting that, okay, we have 10 states as a prior, and now we would like to learn the best possible clustering. And we can train the model even with expectation maximization algorithms. But again, that is left for our future work. So the other application, as I mentioned, is language models for task-oriented dialogue system. So usually, to train a task-oriented dialogue system, the training data looks something like this. The user utterance with some annotation, and then system responses with some belief state. So user is looking for a guest house with free Wi-Fi, so the system should respond with guest house, 33 guest houses, and internet, and then the conversation goes. And usually, since this is a sequence of conversations, we can flatten it and make it into a very long string by introducing some special tokens like user boundaries, belief boundaries, action boundaries, and the response boundaries. So by making it into a very long string, we can convert the task-oriented dialogue system into a language modeling task. And since we have language modeling tasks, we can use the model that I have described, and we can train for simple language modeling, that is predicting the next token given the past. So in this, we did some experiments. Most of the time, we were trying to set up the baseline and get it to work. So our baseline is based on UBAR, which stands for user, belief, action, and response tag, which is what I've shown in this case. So the baseline we were trying to replicate actually reports around 52% of accuracy. So in this case, the goal accuracy is somehow related to how well the system is able to predict the dialogue state, that is, get all the domain correct, intent correct, and the slot values correct. We did some experiments trying to replicate the results. We have around 10% degradation than the published one. And we also tried to do some experiments with the language model fine-tuned for this context. It did not result in any reasonable numbers, and we are investigating, and that's why it's blank. So what next for the generative models for dialogue representations? So since it is heavily dependent on the design of the architecture that conditions the context encoder and the decoder, we need to explore it more carefully and introduce our prior knowledge about the conversations or dialogue or the domain into account. And we can adapt the family of dynamical variational autoencoders for dialogue modeling, since these are very well studied in the area of speech processing in the continuous domain, and we can actually use them in the context of discrete tokens, which is our dialogues. Again, once we have a very good embeddings, we can actually evaluate the quality of them on downstream tasks that David and Sergio presented, which is part of the KA embedding framework. And then finally, once the language model is aware of the context, we can even use it for long conversational ASR. So any questions until now for myself, Martin, or Gabor? So I will pass it to Martin to continue.
Thank you. Hi. So let's start with something you probably know before we get into something you don't understand. You probably know this architecture. This is wave-to-vec. You have these latent encoders. You have this feature extractor to latent representation, quantizer, and the mask transformer. So why this architecture used for speech could be used for dialogues? So in real world, we have labels that are usually missing or not aligned for transcription. If you want to model actions taken during calls with some helpline or selections from database. So we would like to align them somehow, and also the transcriptions or the conversations are really messy, a lot of repeating stuff and not useful information. So we would like to, in some unsupervised way, extract these features, and then having ability to fine-tune on small amount of data to our proper task we would like to learn. So here in the beginning, we started with really simple architecture where we, instead of the feature encoder, we use Todbert utterance embeddings concatenated with speaker information and slot labels. So we have some sort of information about the utterance, and then we also train them in the mask and quantized way to learn these discrete representations, categorical, which can be then classified. So what we also find was interesting during the training, we use these Todberg utterance embeddings. Martin said there was like good improvement when we used longer context, but now actually it performed much worse. The one possible explanation is that when we use all the previous context, the embeddings are quite similar for this training, so it's not training well because we need to separate them. So the context is learned during that. So just to have quick recap how the quantization model works, you are sampling and then using separate code words or code books from which you create the final representation. So just for sanity check if the unsupervised learning works, here I just show here the code groups each has one word, like which is one hot encoded. So if we like project into like from each code word, then we have some grid which we can visualize. So just to check the visualization of if we embed all of the utterances from the validation set and project them into this space, it seems at least the representations here is for users is blue and for user is red, for system is blue. It separates them, so it has some sort of notion which were used for the system and for the user. And also there is like size, is representing how many utterances fell into this representation. So another way to check like quickly how it works is visualize them by time, like the color shift is average time of the code representation of all the utterances that fell into that code representations. So we see there is actually some separation which seems separating somehow well, and then we can just check if there is, if we look at all the representation that fell into this, all the utterances that fell into this, they seem somehow, they lie here, for example, similar about expensive restaurants, or here we can see like some cluster that's probably the final response, which also correlates with the color of it. And here it just answers about the train departure. But some of these clusters seems to, for some reason, contain or collapse multiple different answers that I didn't find common domain. So then if we, sorry, back. Yeah, so if we wanna to visualize that in graph where we create these representations and connection between them by average time and connections, it doesn't really look that good because you again get a lot of different states that are hardly badly described. Here I used some large language model for summarization of the sentences that fell into that. So it seems like this method could be good to explore further, but this is how far I got. And now just to summarize all of this, what we talked about, what we found out is like almost everything works on multiverse, but almost nothing works on real call center data. They are too clean, they are limited domains, and usually they are now contained in all of the trainings for large language models and others. Then the method based on clustering embeddings only, they are not powerful enough to get to the real deployments because we need some other methods that would remove the non-informative text or clustering based on information slots and semantic similarity. Also, it's really hard to preset the optimal number of states for the clustering method. And if we wanted to use slots, the number of states, or really in general, it grows exponentially almost. So there are these problems, but I think that's good for now. Are there any questions or? Yeah, sure.
So we know that those clusters in wave-to-wave for ASR are pretty close to phonemes. We do phoneme recognition on those clusters. We have this. We know it's basically doing pseudo-ASR. You showed some examples, but did you actually compute evaluations on how, I mean, if you only use the clusters for intent classification or anything like this? I mean, so we know they can divide user and system, but what are they more in depth?
Yeah, I did this analysis in sort of like a visual exploration of it, and I showed there are like, if I like checked every single like cluster, for example, now, and I made them summarized in this way, you cannot really see here because it like overlaps so much. So I just wanted to see how messy it is if you want to like visualize them one after another. But if you check, like, the summarization usually really contains the information for these sentences that were similar. So that's the, or maybe.
I'm sorry, I cannot parse at all that graph.
Yeah, the graph is just visualization. If we take all of these clusters and then make connections between them by how each utterance from these clusters were followed with utterance from these clusters, and you count them, then you visualize them, and then you order them by time of the average time of the utterances that fell into that cluster. So it was like simple exploration of graph making, but it was really in the end of the workshop, so not many results. Yeah, sure.
Any other question?
So I would like to give talk.
Okay, so far we have spoken a lot about clusters, states, and so on. So I would like to take a step back to try to explain what we would usually do without any of those automatic methods, right? So you have basically a database of dialogs, and you saw this graph in the beginning, which I kind of expect all of you to remember, of course, totally. So what would happen here is that someone handcrafted this graph, right? And what we are trying to do here is to see if we can achieve this automatically, and what would happen if someone has this kind of graphs. You will either go to some analysts or for some further processing. Yeah, and the typical structure that we try to integrate or to visualize in all these graphs is we chose FST to do this because there is a lot of prior work here mentioned at the end on how to use this for dialogue structure discovery, for representations of dialogues, and how to use that and manipulate it to get a much smaller graph that I showed in the last slide. So the key advantages is that it's structured representation. It comes with nice set of functions that you can use for reducing the size of the graph or to visualize, which is great for someone to interpret. And so what were the challenges when we started to try to use FST? So one is like since Sergio introduced a little bit about the toolkit that we are working on. So we chose the Python interface of OpenFST, and then which helps us try use the common operations on an FST to reduce the size of the graph. We also kept in mind that once you do these operations, it is possible that someone would want to go back and forth to see what happened when you apply these operations. So these are kind of challenges we try to address. To just introduce how you would directly apply a set of dialogues and represent it as an FST, here I try to go step by step. So you have at the top is what we would start with, and the bottom is what we would like to achieve. And the magic that goes in between these two is something that was covered earlier and will be covered later by Mira as well. So you have a set of dialogues. Let's say this is one dialogue in the data set. Yes, someone says hello, hello, and there is another dialogue that says hello, but this is user and there is system. The system responds differently sometimes. This could be a person or the system itself. But in the end, both should be classified as greetings. And what you would like to achieve is, in the end, let's say that is, I want to see a typical conversation that happens between the user and the system. And what happens here is sometimes the user is happy, sometimes the user is not happy. So that's what we would like to see. That's the ideal result of using something like this. Right, so what are the technical challenges that you would face? One is once you start this arrow, once you start applying this arrow, you will start seeing a lot of redundancies like this one. Two kinds of redundancies. One is the longitudinal one, or in the same conversation, maybe there is a lot of repetition that you see after clustering because it's the same kind of information. Or you could see similar dialogues that also show similar kinds of redundancies. So you have two kinds of redundancies. Typically, both can be removed with simple FST operations, right? I show one here, and the others can be handled with simple determinization, minimization. I'm sure you'll hear a lot more about it in the afternoon. So for someone who has not seen this before, it's basically when I say removing redundancies, it means that you have three states of the conversation, and you see one following the other, and both are the same. Basically, I would want to delete that state J and just continue with the graph. Probably that was too quick, but this is what we would like to achieve. And what happens in the end is that you have a whole data set of hundreds, thousands of conversations, and you would end up with something like this. And even after minimization, you see it. You have a lot to parse, even for a human. So how can we further reduce it is something that will be covered the next slide. But just before that, to keep the brand ambassador of Kea happy, I have a slide where how you use this in the Kea, right? So you just import with simple interface to import, create a FST from the data set completely, and then you export it for some kind of clustering, and then import it back, remove redundancies, and determinize, right? So that's it from the implementation side of it, but the magic comes next, right?
Hello, so I'm Miroslav again. We experimented with the FST approach with some embedding-based approaches, and I can see some connections where, for example, graphical neural networks could be used or something else, which was mentioned yesterday. But as we got so excited about this slot-based clustering and it's sort of nicely explainable, I spent most of the last week on that. And actually, what we like about the slots, they are explainable, and we have them present, for example, in multiverse, but they raise also a lot of questions. We need to design slot names, slot values, how many slots should be there, and the number plays important role in the overall number of slots we would get from such representation as presented by the paper. And on real-world data, you will need some slot entity detector or something like that. Yeah, so these are another set of downstream tasks. You will have to maybe have your slots designed per each domain or per each topic. And we identified some problems like the state expansion, and then there's no user and system separation in the way they described it in the paper. And it's very specific to given domain. Here is some visualization from the paper when on the left side you have a ground truth graph on a hotel domain of multivos. On the right side you have the automatically extracted using their slot-based detector. I'm having a hard time to tell whether they are similar or not, but we tried to use their slot-based detector on Alomedia's data and it failed a big time. So we said that we will use their named entities as a proxies. I will show it on later slide. So we had several ideas to better this slot progression, slot-based approach. I call it slot progression patterns, but I don't know whether it's a good name. And we were trying to reuse this idea of slot vectors. We tried to address the state expansion and also have some focus on informational flow from user to system or from system to user, and use all of these to detect some subflows in the dialog. And on the way, we defined some dialog encoding based on this slot approach, maybe a little bit different from the slot approach itself. So here we have some example of dialog subflow. You can see subflow is user info. The whole part of the dialog is focused on retrieving some user info, and system then gives acknowledgement to user that he retrieved it. And the things that are that are in the brackets are named entities which were manually annotated by Almedia. Right, so we used these as a proxy to the slot names and slot values. This is view of the same dialog, but we only focus on these slots that are being transferred from user to system or system to user. So we, in the novel encoding, we focused only on the exchange of the information separately for the user and system. We can see that user provides his name to system. He provides his location or the place where he lives, and then system acknowledges the name of the person back. We can get back from the one-hot encoding to and see it as a number, or I've chosen to see it as a letter, and I've made a convention that big letters will be for the flow from user to system, and lowercase letters will be for the flow in the opposite direction. So what we get out of that, we can just look at these slot changes and encode each dialog as a sequence of letters. You, in one turn, extract multiple information, so you will put there all the permutations of such thing, and you will actually get some text corpora, right? And we are quite used to do some things with text corporas. So we can do language modeling. We can, for example, train a tokenizer to detect some substrings, and maybe many other options that people that are smarter than me can come up with. So I've tried to train a tokenizer on top of that. The idea is there when you do this kind of a permutation, I have underlying assumption there that if you retrieve the information name and location in one turn, so user says both information in one sentence, or whether it's in two sentences in different order, or whether system in between acknowledges is, I see you, I hear what you are saying, or whatever, it will actually encode to the same string, right? So this is sort of the clustering we are getting implicitly. I trained a tokenizer. We can see some word piece units that we got from that. There may be some repetitions, and I am making an assumption that if I tokenize some dialog representation, the shorter is better. So the more of big classes I can get there, the nicer subflows I will get out of that, right? And there are some further assumptions I can make, and some of these are really questionable, and let's say it's just for the sake of the visualization, and it's a sort of a hyperparameter or designing the algorithm itself, how to cluster based on this representation, right? So the further assumptions were, like I said, best tokenization is where I get the least number of the tokens or the word pieces, that we can remove repetitions. For example, if we see the GBII, let's say, okay, it's GBI because I don't care whether a user decided to change his name or repeated the information because the system doesn't understood or something like that. And this is also a very dangerous assumption. And then dialog subflow is the other assumption was that dialog subflow is a set of information provided by user, followed by some information or acknowledgement made by system. This also doesn't have to be true in all dialogues, but this is just what I used for this visualization. So the main hyperparameter here is the size of the vocabulary for the tokenizer, right? If you put too little tokens there, you get very fine clustering, where each arc is just one letter or something like that. So that means exchange of one information between system or user. If you allow tokenizer to create a lot of the words or word pieces, you get clustering that will have little states and little edges, but it does not explain the underlying data in any way. So I think I found sort of a sweet spot. Let's not dive deeply into how I did it, but it was symmetric. And we could get from the fully alfold graph, which had 8,500 arcs, to some small graph that had around 660 arcs, but these are not like folded in time or pruned by any probabilities, so there's further pruning possible. And this is some example of the identified subflow. Remember, we have here the translation table that each letter means some slot being transferred from user to system or system to user. So if we have, for example, the arc from 0 to 1 and it says AHI, it actually means that a system provided to user date, organization, person information. This is usually done in one sentence, and it's common starting point in the Allomedia dataset. Like, hi, this is Peter from Allomedia, how can I help you today? But if we look, for example, on another thing, this is this AIKA cluster, we can see that some bigger part of a conversation fall into that, and some of the non-informative terms like got it or something like that are implicitly clustered together with the rest. That makes some sense in the subflow. Of course, I've selected some of the patterns that made some sense, and there are many that might be hard to explain or something, or it will be much worse, yeah, and it's hard how to evaluate that. And for that, we will need some defined granularity of the dialogue, so maybe something like the ground truth graph annotated by human on Allomedias, and do something like bipartite graph and checking which subflows are there and not, and so on. So I think you will have many questions, but bear in mind that I've implemented it on Friday night. So, okay. We can see a lot of further steps, like further filtering, trying different approaches to the creation of these substrings, like different tokenizers. or some encoding algorithms. We would like to see some hierarchical subflows or hierarchical slots. And of course, this is based on the idea that we have slots that actually represent something, and that area is also a research domain per se, like named entity or slot recognition, and usage of LLMs and so on, like Gabor was mentioning. So that's maybe, oh, there's another slide. I think it's a duplicity, right? It's a dupe. Yes, yeah. And of course, maybe talking about that approach, I was just trying to explain the Alomedias dataset. If something like that was supposed to run on the real-world data and adapt to new domains and so on, this will raise a lot of new issues, like with this. Yeah, I forgot how you defined the thing with tokenize yesterday, that it will start to tokenize badly because of the domain shift and so on. Yeah, so that's probably it. I will hand over to... Maybe questions. Yeah, maybe questions, okay.
I know you said you didn't want to go into the details of how you prepared or how you came up with the method for reducing the tokenization or the size of the FST. But could you give an idea of like what kind, is it based on some heuristics on the data or something else? Because I'm trying to understand if there's a new data set that you want to recreate this effort for, what kind of efforts would go into it?
Yeah, so you would have to define the slot names and slot values, right? That's the dictionary you are defining, actually, the words that are exchanged between user and system. So you will have to have some named entity recognition model, but at this case, we are actually not interested in the values of the named entities itself, but we are interested on the categories. So it has to have some sort of notion of categories, and these must be, they must be relevant to your task. So maybe you can do named entity recognition and then some clustering and select some good clustering for your task or your domain. And that's basically it, yeah? Then you can just tune these parameters some way how you cluster these. Like I've made here some dangerous assumptions, as I said. So you may think of your problem whether the order of the information really matters there or not. And based on that, you will get different results. And then by tuning the size of tokenized vocabulary, you can sort of regulate the granularity, and this is also the issue, because you never know what the customer wants to see in the end, how granular the graph should be, right? Yeah, but if you try to use the pre-trained model for slot discovery from the paper on the real-world data, I would guess that it won't work.
I would like to know if you have some special care regarding the differences, because I saw that you removed the repetitions, and probably this kind of information can be considered as noise to detect the intention, but can be interesting to detect the satisfaction of the conversation.
Yes, I guess I've mentioned it even here somewhere. Yeah, we can remove the repetitions, and it should be okay for structure discovery, right? We don't care if a user provided the name twice, he had to correct himself or something. But if we are looking for script adherence, then the fact that he needed to provide info 4 times might be really important for us, right?
First, to quickly clarify for Murray, I think when Mira says he removed repetitions, it's not repeated words, it's repeated dialogue turns. So if you provide your first name and then your last name and then something, those are the repetitions. But Mir, I had a different question. I was thinking about this more like a very core, simple problem where I have strings. Let's say I have 1,000 dialogues, I have 1,000 strings, and then I want to find a finite state machine which accepts those strings and is as small as possible. But if I treat the problem narrowly, we basically first create 1,000 FSTs which accept only one string, take their union, and then you determinize, minimize, and you're done, right? But that doesn't give us insight, it gives you that graph on the left. So we have to do something better than that. So I'm wondering whether there is other literature that you could look at. I was looking to see if Cyril was still in the audience, because this is a core problem, and I think it's even NP hard, but the real challenge is to say, I don't want to accept these and only these strings. I can accept many other strings because this dialogue could go many other ways. But on the other extreme, I don't want to accept every string in the universe, because otherwise your machine is simple. One state and as many arcs as there are letters and you're done. Between, there is a good compromise. And for example, one of the things you mentioned was you wanted to know subflows. So perhaps you could look for longest common substrings and find what substrings are there in many things and collapse them into a symbol. So this comes down to heuristics.
Yeah.
And I'm wondering whether there are other people in the audience who know how to tackle some of these, because I know a few papers. And by the way, the Lucas team is going to have exactly the same problem. They're going to have names in the audio, and there are going to be many phonetic transcriptions of the name, and they want to come up with one pronunciation, maybe a few alternatives for those names. So, yeah.
For me, some of this is actually, if you see a graph like that, it doesn't actually. I have slightly different decoding, right? Because AHI doesn't mean I only accept the string AHI. It accepts every combination of that. So in this way, it's not like normal FST, and the sort of things you were talking about is encoded in there. But yeah, you are right. If somebody has cool ideas to what to do with representation like this, you are welcome.
Well, I don't have answer for Sanjeev, but I've noticed actually you're struggling because it seems, it's complicated. The problem is complicated, and I was just wondering. So it's a question/comment that maybe the issue is that FST is just too limited to represent the full extent of the dialogue. Maybe it's not just a regular language, but you need something like a context-free grammar or something even higher. So maybe actually one of the problems arises because the FST is just too limited. But of course, that's a half. It's not a solution because CFG and others are even more complicated to use. But I don't know. It's just a thought here.
Yeah.
I don't expect answer. It's just a comment.
Okay.
We're kind of assuming that it's a regular language.
I just want to comment that all the conversation have some finite length. And there is always the trick, if you just increase the length of your regular expressions, or so it's.
But it can even for. So it's true that even since you have finite lengths, your model, even though it's let's say CFG, then after the composition will become a FST. But in this case, the memory can go up, and you probably end up having a FST which is like trillions of states, and it can go very, very quickly. So, but yeah, yeah.
Maybe one thing I like to mention: the Almeida dataset is really closed domain. It's just about payments that didn't go through, right? And we still end up with quite a big graph that needs further pruning. And I wouldn't jump to very big conclusions here.
Okay. No, I was also thinking of Desha's question. So that's the core problem where you have to use some heuristics. There's one paper I'd remembered from long ago by Andreas Tolke. It's in the late 90s, where he was solving this problem, where he was trying to take, he thought of them as HMMs, but basically same thing. And he was trying to find an HMM topology that explains that subsumes a number of other HMMs. Yeah.
I think that one of the problems is that we don't know the granularity we are looking for an explanation for the data, actually, and the granularity should be something that the user provides, maybe.
Any other question?
So I'll hand over to Peter, and that's it.
So okay, I will conclude the talk of our team. What I saw, we really managed to create very powerful team of people, and what is even better, the people wants to collaborate after the workshop, really go in this direction and try to solve it. We wrote tools that can be used, that can simplify the future research. So you saw that it is a very complex task. There is implemented, there is data question, there are embeddings, there are, let's say, core methods, but we saw that the methods itself are not enough themselves. We need to combine them. So we have approach how to do it through finite state graphs. We have this, and I hope that everyone from the research community will be able to use it. We managed or we mapped the areas. So at the beginning when we came, I think that the view of everyone from the team was very limited, and we managed to enlarge it. So if we have a huge amount of resources on the communication channel, and we would like to summarize it and to present it to community. Yes, so there were many works. For example, this Mira works, this wave-to-wake works that we started, but I think these are promising directions, and we can continue. There were companies in the team, and they were asking what we can use, what is the nearest thing that we could put to our product. So we would like to prepare a plan or a recommendation for the companies, so that they have some outcomes from this workshop. We were considering, you see that we have tasks, we have some data, so we were considering whether to organize a challenge. There is a call for the STC 12 challenge now. We may respond, let's see, we either respond if we consider this is too quick, we may respond to some later challenge. And as I said, people would like to collaborate. We just got new research projects, so we are sure that at least some members of the team will be collaborating with the founding, and yeah, we will look for ways how to continue. So I would like to thank the team. I would like to thank organizers of the whole workshop. I think it was a wonderful experience for all of us. So thank you. So not sure if oh, okay. Yes, so I was asked to show some photos. So this is our team, and on the right, you can see how we work hardly in the lab, and here is our other photos. So you can see that we know how to rest, how to have parties. So as I said, it was a wonderful time here. So thank you, and questions?
then thank you, and let's break for lunch. And to the online guys, we are going to switch to another channel at 2 o'clock.